Now in this lecture we study the successive approximation. In the last lecture we have studied the flash. Now flash required only one clock pulse to get the analog output to the analog input to the digital output. Now coming to the successive approximation, this is the most popular ADC. Now here it is also converting the analog signal into the digital signal by approximating the given analog signal into the few digital inputs. So how it is doing that, let me explain by using the diagram. Here also we are using the one comparator. Now this is one comparator. For this, here we are applying the analog input. Now this analog input is compared with the n number of digital outputs, what we are taking here, how many number of digital outputs we are taking. So that will be converted into the analog signal, and these two signals are compared. So when both the signals are matched, then it will display those digital signal at the output. So now for that we are using the successive approximation register. Now it is having the start of conversion and end of conversion and the clock signal, and it is having the some digital. So here it is MSB bit and this is the LSB bit. In between we have digital outputs. Okay, now here these digital signals are given to the again DAC, digital to analog converter. So whatever the analog signal we are giving, that is approximated by the n bit digital signal. Now if I take to understand the concept easily, now I will take 4 bit. Now here it is a 4 bit register, so it is generating the 4 bits. So first it will set the MSB bit high. Now here I will take the reference voltage to understand the calculations easily. I am taking the 4 bit register, so it is having the 0002 all ones, and here I am taking the reference voltage such that my step value is equal to 1 volt. So for easy calculation purpose I am taking the step value as 1 volt. Now at the beginning, now if I switch on, now here this is called the V reference, and now you can say VD digital. Now digital signal which is converted into analog signal, so that is VD. I am taking the name, I am giving it as a VD. Now if you switch on this, then first at the beginning it will set the MSB bit to high. Now if I am taking, this is a 4 bit register, so MSB bit is high and the remaining 3 bits are 0. Now this digital data is given to the DAC. This DAC is converting this digital to the analog signal. So to calculate easy calculations, here I am taking the reference voltage as a 16 volts, so that the step value is 1 volt. So now for this the equivalent analog signal is what? 8 volts. Now for this the equivalent signal is 8 volts. Now this 8 volt at the beginning, always when you switch on, then first it will set the MSB bit, and this magnitude is compared with the analog input. If the analog input is greater, more than this 8 volts or this converted analog signal, then one more weight is added to this one. Now for example, if I wanted to weight the few vegetables, now this is my balance. Now if I wanted to measure the vegetable, now here vegetables are there. So now I have taken the 2.5 kg weight in this plate. Now if I wanted to measure this, then how can I measure? First I kept 1 kg. 1 kg weight. Now here the vegetable weight is more, that's why I needed to add one more 1 kg weight or half kg weight. Now still if my weight is, now vegetable weight is more, then I need to add one more weight. Like that, what if whenever these two weights are same, then at the time I have to stop adding the weights on this plate. Now this is about for 2.5. Now for example, if this side I have vegetable weights are only half kg. At the beginning, now here I kept the 1 kg weight. Then what? Now if this vegetable weight is less, then I need to remove this 1 kg weight and put half kg weight. So if both are equal, then I have to stop putting the weights over here. Now this is the same concept I am going to use to measure the analog signal. Whatever the analog signal we need to convert into the digital. So now here I have, now for example, to understand the concept easily, I am taking the 11 volts analog signal at the input. Now after applying the 11 volts, if I switch on this, then the first, initially what it will do, for any voltage, initially first MSB bit will be set. So now MSB bit will be set. Now here it is 1. So this is converted to the analog input. Now here this is 8 volts. Why I got 8? I have taken the reference voltage such that my step value is 1 volt. Okay. So for easy calculations I have taken like this. It is not necessary that we need to follow this. So how much the reference voltage, depending upon that I will get the equivalent analog voltage over here. So okay, now for this, now if I got 8 volts, now which is more? Now input analog value is more. If this analog is more, I have to keep this MS bit as it is and need to set the next MSB bit to the 1. Now this bit is 1 and 0, 0. Now after that this is applied to the DAC. Now what is the equivalent value for this one? This is nothing but what? So 8 and 4, this is the 12 volts. So now here it is a 12 volts. 12 volts is now comparing with the 11 volts. Now the input analog value is lesser. So now what the successive approximation will do? It will keep the MSB bit as it is and it will reset the next MSB bit and it will set the other if I take this as a B0, B1, B2, B3. So it will reset the B2 and it will set the next MSB bit, no, nothing but a B1, and this is nothing but what? 5 volts. Now this time it will compare 5 volts with 11 volts. So now 11 volts is more, that's why it will keep this bit as it is. Now if the input analog is greater, so then it will keep the previous bits as it is and it will set the next bit. If the analog input is lower, then it will reset the recent MSB bit. So whichever bit is set recently, that will be reset to 0 and the next MSB bit will be kept to 1. Now it will keep this bit as it is and it will set the next bit 1. Now what is the equivalent value? This is nothing but what? 11 volts. 8 plus 3. It is 11 volts. Now if this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So this magnitude is 8, this magnitude is 2, this magnitude is 1. So 8 plus 2 plus 1 is nothing but what? 11 volts. So when both the voltages are equal, then so end of the conversion bit will be raised and it will stop the converting, and whatever the bits are set, now here 1 0 1 1, that will be displayed at the output. Now here this is nothing but what? Digital output. So whatever the register, successive approximation register values are there, that will be taken out. Now I will take one more example. Now here how many number of clock pulses are required to convert this analog to digital? So 4 clock pulses are required. Now this successive approximation takes the how many number of here digital bits we are taking, those many number of clock pulses is needed to convert this analog to the digital. So now if I take one more example, now if my analog input is 7 volts, then so at the beginning when we switch it on, when we switch on this and start conversion button is given, start conversion signal is given, for the first clock pulse it will set the MSB bit 1. So 1 0 0, it is nothing but what? 8 volts. Now this 8 volt is compared with this 7 volts. Now the input voltage is less, that's why what it will do, so here it is less means what? The successive approximation register will what it will do? It will reset the MSB bit and it will set the next bit 1. So now what is the equivalent value? This is nothing but what? 4 volts. Now 4 is compared with the 7. Now 7 is greater. So that's why what the successive approximation will do? It will keep the first 2 bits as it is and it will set the next bit to 1. So only say next bit is 1 and the last bit is as it is. So now what is the equivalent value for this one? This is a 6 volts. Now 6 volt is compared with the 7 volts. Again the input value, analog input value is more. Then the successive approximation register will keep the first 3, the most 3 bits will be same as it is, and the least significant bit it will keep it to 1. It's set to 1. Then the value is 7. Now 7 and 7 both are equal. Then it will stop the conversion, and whatever the bits are set on this register, it will be displayed at the output. Now like this, it will convert the analog input to the output, digital output by comparing this analog inputs to the some n-bit digital inputs. So this is about the successive approximation. Here how many number of clock pulses are required? So how many number of bit digital outputs we are taking, those many number of clock pulses are required. So this is about the successive approximation. With this we finished the unit 5. Thank you.